Welcome to my talk, which is on a SuperMUC project on atmospheric chemistry and climate. I will show results from numerical modeling of the impacts from road traffic and aviation emissions on the atmosphere and climate. My name is Sigrun Matthes, and I'm from the DLR Institute of Atmospheric Physics in Oberpfaffenhofen. The results I'm showing are part of DLR projects, Track and Echo to Fly, but also of European collaborative projects like Fly ATM4E, Acacia, Alarm, and CLIMOP. The outline of my talk will provide you an introductory information on how the aviation emissions and transport emissions act in the atmosphere, and the main focus is on the CO2 and non-CO2 effects. And in fact, I will start with showing you that aviation, by the combustion of fossil fuels, is emitting CO2 and water. And together with the combustion process, there are other non-CO2 emissions, which are namely the nitrogen oxides, the NOx, the carbon monoxide, the unbound hydrocarbons, but also soot particles. So if we look at the atmospheric impacts, there is on the one hand side, there is the CO2, which is known as a greenhouse gas, and where the atmospheric concentration is increasing steadily, with aviation contributing about 2.5% to the anthropogenic CO2 increase, while on the other hand, there are the climate impact of the non-CO2 effects. The visible non-CO2 effects are the contrails and contrail cirrus, but there are more. There is also water vapor. There are chemical effects due to the nitrogen oxides and a atmospheric chemistry, which causes ozone formation and methane destruction, but also aerosols and cloud effects. So overall, the IPCC, the International Panel on Climate Change, has evaluated the radiative effect of aviation. And in fact, on the figure on the left, you see that contrails and CO2, they contribute to the warming, and they are shown as each line is an individual effect. When we go further down, we see the nitrogen oxides effects, which are on the one hand side warming, shown by a red bar, but on the other hand side, there are also cooling effects, which are kind of compensating. And there are further effects which have to be considered. If we take a look at the overall impacts, if we take a look at the overall impact of the non-CO2 and the CO2, in fact, you see that non-CO2 effects amount about half, 50% of the aviation total climate impact. This is a radiative imbalance, which means like a radiative forcing, which is in watts per square meter. If you want to translate this to an atmospheric surface temperature change, this is which is what is shown on the right. So if you bring this forcing to the atmosphere, you see that to this temperature change, aviation is contributing about 5% in the year 2018, with the total impacts with about 50% originating from the non-CO2 effects. I will now show you how we are modeling, how we are doing the modular approach in our modeling system. And in fact, our modeling system is relying on, we have the modeling system EMAC, and we have a discretization of the Earth's surface, and we do model the processes on a grid scale. Additionally, we have the possibility to do an online nesting. So in this global instance, we can nest regional instances and zoom in specific regions. What is particular here and what is unique is that we can use in both model instances, we can be using the same submodels. So that means we have atmospheric chemistry and tropospheric and stratospheric chemistry, which are similar. And we can also use the same diagnostics. So that means we can have the same sampling, and we can have the same diagnostic modules, which we are using in both modeling domains. This leads to us to the possibility to construct the whole model setups. And this is from a chemistry climate model initiative, just by way of example, to show you how such model setups and model experiments look like. And in fact, we are having also a vertical level. We have also vertical discretization of the domains, and we do metrology nudging, and we have online and offline emissions, and a lot of atmospheric chemistry, and the processes are represented in our simulations. So what is particular here, and what is in fact the central central element of our modular approach? This is in fact that we are having a kind of middleware in it. So we are having shown in blue in the central part, we have an infrastructure which is connecting the base models on the one hand side with the messy submodels on the other side. So that means we have a kind of pinhole searcher which allows to get via an interface the basic variables from the base models and link this to the messy submodels, which are then developed independently, and you can select them along your needs for a specific simulation setup. And what is here really central is this kind of structured modularity in the whole configuration system of the messy system. How are we then doing? And in fact, by way of example, I want to show you the expansion of a Lagrangian transport scheme. And in fact, in the atmosphere, transport is, of course, one of the central mechanisms. So it's our model system allows to have different transport schemes available and use them and see how to best model the behavior. So we have the system Attila, and if you extend it, you also have to evaluate it. And in fact, this is what is done here. We are using atmospheric observation of radon and the age of air. And what you see for the radon, in fact, you have large concentration over the continents, which is shown here on the left in the red colors. And you are having ground-based stations, and in the middle plot is shown how the model values agree with the observations. And in fact, you see that you have agreement with the conservative and the new different Lagrangian schemes within a factor of 2. So that means that your novel transport scheme satisfies the overall characteristics of the atmosphere. If we then look to the vertical, we can use the age of air, which is an atmospheric parameter, to indicate if the transports are realistic. And in fact, what you see here, by following the red curve, you see that with the Lagrangian diabatic, which is the novel scheme, you are well representing the vertical and realistic stratospheric transport. So this is what you have to do if you work on the original modules before you can make it available within this infrastructure. An application of such a Lagrangian scheme I want to show you now. And in fact, we are using it in order to work towards climate optimization of aircraft trajectories. This is work which is done in a European project, and in fact, this project is RECT4C and ATM4E. And this is, we are developing information where the atmosphere is in particular sensitive to aviation emissions. What is shown here on the top is the weather data and the ozone correlated effects. So here is shown the zones where you have the high wind speeds and where you have the geopotential. And you see, if you look to the top patterns, you see from these Lagrange, from following the emissions of aviation, you can identify those regions where aviation emissions have a large impact, indicated by the brownish colors, while other regions have aviation has a lower impact by the clearer regions. And these lighter regions are those which are less sensitive to aviation emissions. So less ozone is formed, less forcing is caused there. And if you exploit this, and this has done in a case study for the European airspace, by evaluating individual trajectories to see if there are alternative solutions where you can mitigate climate change, you can see on the left example that in the left example, you see the left column is the total effects, and you see it has a strong green contrail cost effect, while red is the nitrogen oxide and CO2 is in blue. By changing the trajectory slightly, avoiding a supersaturated region, you can avoid the contrail warming and you can reduce the climate impact in this situation considerably. While on the right trajectory, there is no contrail region, so no green color, but you can see by changing the trajectory alternatively, the red contribution to climate change caused by the nitrogen oxide can be reduced, and you can reduce by then 9 or 15% the climate impact of this aviation movement over Europe. Beyond the climate impact simulations, we are also doing assessment of the tropospheric ozone, in fact, talking about air quality. And in fact, the emissions of the reactive species over Europe are causing an ozone production, and which then reduces the air quality. By our model simulations, we can also model this, and we use the regional global system, which allows us to zoom into specific regions. And in fact, what is shown on the figures here is the contribution of the road traffic to the surface ozone levels. And you see that overall road traffic contributes about 15% over Europe. And you see the global instance, the coarser resolution, EMAC, compared to the higher resolved simulations with the Cosmo model. And in fact, by zooming in with the Cosmo model, you see that the aviation, that the road traffic signal is changing depending on the resolution you're using. The orders of magnitude stay the same, but the signals get slightly larger. And with such assessments, you can identify the contribution of a specific sector to the overall ozone levels observed. So, what are the challenges we are facing in our domain? And in fact, from the societal needs, there is the requirement for future climate chemistry simulations to be even more resolving processes, longer simulations, or even seasonal forecasts. And this is causing the challenge to have higher spatial and temporal resolutions, for example, to also enable convection resolved modeling. And with such high resolved resolutions, you have a large burden for the communication. You have to, if you do massive parallel computing, you have a lot of communication loads, and you have to be effective, and your domain decomposition needs to be done in a way that you can reduce the communication, but you also have to assure that the scalability, depending how you decompose your domains. Another development we are also trying to face is the usage of the GPUs. And in fact, this in many domains requires the development of new algorithms because the legacy codes are not possible to be run efficiently on the graphical processing units. An interesting feature is also the adaptive grids or non-irregular grids. Such grids can allow you to be, again, zooming in and have a dynamic grid, but this is a real challenge for the future climate modeling. And finally, there is one architecture element why the current computing resources are having more resources and less memory. The climate change is different. Climate change simulations are different. So we often use a lot of storage, and this is creating a real challenge. And with this, I want to briefly show you the references and the papers where you can see more details on our results. And I want to conclude our study with a summary giving you the overview on the results. And with this, I would like to thank you for your attention.